Good day, everybody. My name is Dominic Ryan. I'm a graduating senior here in 3 weeks, and today I'm very excited to present you guys with my findings from this year's HURA grant research project. The title of my research project is Understanding How to Detect Oceans on Exoplanets Using Spectral Principal Component Analysis. A little bit of a tongue twister. So what the heck does any of that mean? Well, in science and especially in astronomy, my field of study, there is a big push on understanding how life forms and the possibility of it existing outside of our solar system. So, life itself is a very precious thing. As far as we know, we are the sole possessors of life in the universe as of right now. And there's a lot of different factors contributing to this. Of course, being a safe distance from the sun, having a large enough sun to sustain us, having a good atmosphere, and obviously one of the largest in both importance and size is our ginormous oceans that cover our planet. So what method of study did I use to detect oceans? We use something called principal component analysis. So basically what this is a method of data kind of extrapolation where you take a set of data and you pull it apart into its most relevant components. Dr. Robinson, my advisor, summarized this very well to me when we first started working together with a car metaphor. If you have a car that's really, really bumpy and you're wondering what the cause of it could be, you can use PCA on this bumpy car in order to pull out the components in order to source where the bumpiness is coming from. Your first component and your most prominent source of bumpiness could be because your axles are misaligned. Your second component, the second most prominent source, could be because your engine's misfire, and so on and so on. It can be as robust and diverse as it needs to be. So we use PCA on Earth spectra, most importantly, Earth reflectance spectra. Basically, when the sun hits the Earth, a bunch of different sources from clouds to the ground itself reflect light back. And some of that light is actually reflected from the ocean if hit at the proper angle. This phenomena is known as glint, which is highlighted in figure 1. You can see it in the red circle, and it's actually observable from outer space. So what we did is we took this reflectance spectra from a variety of different inclinations and different number of observations of Earth and applied PCA on it in the Python programming language in hopes of seeing if we could pull out a relevant spectra that looks like Glint's known spectra, which is highlighted in figure 2. This is the known raw data spectra of what Glint looks like. And fortunately enough, our results were very, very successful. As you can see in figure 3 and comparing it to figure 2, you can see the stark resemblance between our reflectance spectra PCA component 1, which shows it's the most relevant source of reflectance, compared to the glint spectra, which is really, really awesome results for us. And you can see in figure 4, those are the components 2 and 3 for the different inclinations that chalk up to be a different array of reflectance sources. We didn't get down into determining exactly what they are, but we can most likely say that is most likely from clouds. And then at inclinations of about 45 degrees, it kind of falls off and merges together in both component 1 and component 2. So that inclination doesn't work all that well. So the reason we use different inclinations of observation on the Earth is because sometimes when we're observing exoplanets, we don't get a straight head-on image of the planet. So we might have to work with a smaller angle of observation, which shows that even with smaller angles of observation from 60 to 90 degrees, we can get very promising results. Another way of limiting the data to see how successful this method was is we reduced the number of observations. For our first set, we used 10 observations just in case to get like a nice high number in order to observe glint. And we found all these to be successful. And then we limited the number of observations just in case telescope data up in the future results in less observations. We could still see that even down to 2 observations, we are still able to observe glint using this PCA method. So with all of this in mind, it's really safe to say that this is incredibly exciting because it's a very useful and very, very easy method of determining quickly if a planet has a sustainable ocean on it like our own. There's a whole different bunch of ways this can be further studied on the success of maybe detecting entire liquids versus just H2O in our oceans. further observations on where the threshold between 45 degrees and 60 degrees is on determining exactly where it drops off and PCA is no longer detected. But for these preliminary results, it's very, very wildly successful and extremely exciting for future exoplanetary studies. Thank you guys so much for watching. Thank you guys for giving me this opportunity to present. I'd also like to thank Dr. Tyler Robinson for his tremendous help for the past year and pushing me to new limits as a young scientist, and of course to the Hooper Undergraduate Research Award for giving me this exciting opportunity to present to you guys. I hope you guys all enjoy the rest of your day. Thank you so much.